So last week we started with a new module, which is the module number 5, microwave semiconductor devices, right? So let's proceed further. So what we basically learn here is about semiconductor devices, right? So as we saw during the Second World War, that is the early generation of microwaves were using klystrons, magnetrons and traveling wave tubes. But what was the problem there? That they were very bulky, right? So obviously we require something which is compact, right? So they were very heavy and bulky. Apart from that, they required a very high voltage. So if you think in terms of the DC voltage which is required for the electron beam, it is in the range of kilovolts, and in some cases it might go to megavolts also. So this is a huge amount of voltage, right? So obviously there was a need of semiconductor devices. So as such, a wide range of microwave semiconductor devices were developed since 1916s for many applications which are mentioned here. And in most of the low power applications, solid state devices now have replaced electron beam devices. So what were the advantages? So these disadvantages were becoming advantages here. Apart from that, they were highly reliable and having low cost also. So this is the reason we study this module, which is microwave semiconductor devices. But you should remember that even though we are migrating from microwave tubes to microwave semiconductor devices, it is not the thing that we don't use these tubes. These tubes are used even today, but mainly they are used for defense applications. Okay. So what we studied here is mainly Gunn diode, impact and trapet diodes. Okay. So pin diodes are used for attenuation, modulation, switching, phase shifting and limiting. And vector diodes are used for frequency multiplication, parametric amplification and tuning. So tunnel and Gunn diodes are used for oscillation, while impact and trapet diodes are used for amplification as well as oscillations. So first which we studied was varactor diode. So why it was called as varactor diode? Because it is has the name from variable reactor diode. So it is nothing but a voltage variable capacitance of a reverse biased PN junction. Okay. So as we saw that the capacitance varies. So as you increase the width, what will happen? The depletion layer will increase. So that depletion layer increase, that is the distance between the dielectric increases, right? So it is nothing but the capacitance is changing. So that's why it is a voltage variable capacitance, and that's why it is called as variable reactor diode. Okay. So Cj is inversely proportional to W. So then we saw the capacitance is maximum for zero bias. That is when you are giving a zero voltage, the capacitance is maximum. And it varies inversely with the applied reverse voltage. That is when you give a negative voltage here. So this diode is reverse bias. So then you have for the maximum negative value, you have the minimum capacitance. Okay. So the usual reverse voltage swing is between the reverse saturation point, that is maximum capacitance, and the point just above avalanche, that is minimum capacitance. As I said, avalanche devices we have to study it. So this is the equivalent circuit. So then we went to PIN diode. So what was the construction? It consists of a highly doped P-type semiconductor material. So this plus sign indicates highly doped, and it has a extremely high resistivity intrinsic semiconductor material here. So this is the I here. So it is between PIN. That's the why the name PIN diode, right? So then this is depicting that the highly doped regions have low resistivity, while the lowly doped intrinsic layer has the high resistivity. So we have two types of PIN diode, pi type and V type. So in pi type, heavily doped P and N regions are separated by an unusually lightly doped P type. While if it is separated by a N type, lightly doped, then it is V type. Okay. So then what is the operation in the reverse bias? Obviously we will have high resistance. So we have already seen this. But what happens when a forward bias is applied? Carrier injection into the I layer takes place. Right? So electrons are injected into the I layer from the N layer, because for the N layer, what are the majority carriers? Electrons. And holes are injected from the P layer. So what does this do? It reduces the resistivity, right? So above the equilibrium, once it reaches above the equilibrium, the resistivity of the layer drops as the forward bias is increased. So low resistance is offered in the forward direction. So it took the example of a coaxial line such that it acts as a switch. So we have already done this, right? So then this is the equivalent circuit, and this there should be a line here as I said. So then its applications are switch, SPDT, single pole, double throw, phase shifter, and amplitude modulator. Then we went to tunnel diode. It was called as Isaki diode. Why? Because it was invented by Isaki. So it is a p-n junction diode again with extremely heavy doping on both sides of the junction and an abrupt transition from the p side to n side. And this is the reason we use energy band diagram to understand this. And what is the peculiarity of this diode? That it has a negative resistance or a portion of its VI characteristics. So this is the negative reason. So as the voltage is increasing, the current is decreasing, right? So usually we have V equal to plus IR, but what is happening here? V equal to minus IR sort of. So that's why it is called as negative resistance region, right? So then we had seen, so this description is just the reading of the graph. So when you have a reverse voltage, the current is in the negative value, it is increasing, right? Then in the normal forward bias, it increases up to a point Vp, which is called as the peak point or the peak voltage, where you get the IP peak current and the peak voltage. So then if you increase above Vp, the current decreases. So this is the negative resistance region, and it keeps on decreasing until it reaches the maximum negative value, which is the valley point. So you have the corresponding valley current and the valley voltage. So this is called as valley point. So above this valley point, again it starts increasing, right? So this is the operation of a Gunn diode. So then we have unbiased V equal to 0. So under unbiased conditions, the electron energy of both p side and n side line up at the same Fermi level. So since Fermi level are the same for both the points, so this is in equilibrium condition. So the net tunneling is 0. There is no transfer of electrons. So then when we have V lies between 0 and Vp, what happens is the n side level must shift upward, right? So this n side level shift upwards. So this this is n side, right? So this level from the conduction band shifts upwards. So that is shown by a dark gray line here. So since this shifts upwards, what will happen? This electrons can tunnel through here, right? So this is shown that tunneling. So tunneling can happen in this. So due to this, the forward current will increase as bias voltage increases. So this can reach up to a maximum point when this dark gray region reaches this Fermi level, right? So when this reaches this Fermi level, that will be the peak point, right? So that is this peak point when V equal to Vp. So we'll get a peak voltage and a peak current, right? So then when Vp is greater than V but there is less than the valley point, so this obviously this will go on decreasing, right? So that is the reason this in this graph this voltage goes on decreasing. So in this region you find the negative resistance region when V lies between Vp and Vv. So then when V is greater than Vv, so this gray part goes above the Fermi level, and because so what happens, no electron can tunnel through the barrier and tunneling current drops to 0, right? So that is what happens here. So then we saw the applications, right? So this is what we saw in the last lecture. So this is what I revised it for you. Yes, I am recording. Just minimize this. Yeah. So let's go further. So very important question from the exam point of view is Gunn diode. So usually you get a question like write a short note on Gunn diode, 10 marks, or explain the list the modes of operation of a Gunn diode and explain any one mode. So usually uh, explain the stable mode. So let's see what is it. So these are called as transferred electron devices. The electrons are getting transferred, that is the reason they are called as transferred electron devices. So these are bulk semiconductor devices having no junction or gates as compared to our normal p-n junction diode. So what happens in the p-n junction diode, we have a junction or a gate. So that is not the case here. So essentially this slide describes the difference between the transferred electron devices and the normal diodes. So you can expect this question in the exam as well as a viva. So if you see the TEDs, which are transferred electron devices, they are transferred fabricated in fact from compound semiconductors such as gallium arsenide, indium phosphide, or cadmium telluride. But usually the GaAs is commonly used. Okay, and what is used in Gunn diode is germanium or silicon. So that is not the case here. And the TEDs operate with hot electrons as compared to warm electrons which are used by transistors. So Gunn diode is an example of TED which exhibits again negative resistance regions which we saw in tunnel diode. So we saw a negative resistance region here, right? So same thing we will again see in Gunn diode. So one thing which you need to understand is Gunn effect. So it was observed by J.B. Gunn in the bulk N-type GAS. So again you see GAS, gallium arsenide, is used here. So you observe that above some critical voltage. So we'll again see what is this critical voltage, 2 to 4 kilovolt per centimeter. The current in the specimen becomes a fluctuating function of type. So after a certain voltage, even though you are applying a DC, what is happening? It is depending on type. So that is what it is was observed by Gunn. So this effect is called as Gunn effect, and that is the reason this Gunn diode can be used for generating oscillations. So that is what is mentioned here. And negative resistance will get manifested under itself in the certain conditions. So what is happening, that we'll see in the further slide. So that theory is explained with the help of Ridley Watkins Hilsum theory, which is RWS theory. It is also called as two valley theory. So some materials like the N-type GAS show two valleys in the conduction band as shown here. So you see this is a again an energy band diagram. So in the conduction band of GAS, what you see is two valleys. So and this is the lower valley and this is the upper valley. They are separated by 0.36 electron volt. So this lower valley has a lower effective mass, and since it has a lower mass, what will be the mobility or the traveling capacity? It will be higher. But since this has a higher mass, it has a lower mobility. Okay. So in the two valley model, there are two regions in the conduction band in which charge carriers can exist. So that is what I have mentioned here. So these regions are designated as valleys and are designated as this is the upper valley and this is the lower valley. So according to RWS theory, so this is a theory which is given by RWH people. So it has a lower effective mass and consequently a higher mobility. So the vice versa is happening here. So that is what I told you. So how these electrons get transferred from the lower valley to the upper valley, that is essentially the operation of Gunn diode. So let's see that. So when in the applied electric field is less than the lower valley electric field, that is EL, then electrons will occupy states in the lower value only. Okay, so when E is less than a certain value EL, electrons will occupy states in the lower value only. So what will happen? Because of this, the material is in the highest average velocity state. Why in the average velocity state? Because it has a lower mass in the lower value. So due to the lower mass, the electrons can travel with a higher velocity. So that's why the drift velocity increases linearly with increasing potential. So we know from basic electromagnetics that if electric field increases, the potential increases. So that is what is here. So because of this, the current density also increases, and hence we have a positive differential resistance. That is, we have a positive resistance region. So as the electric field increases, the resistance also increases. So, but when we have the electric field which is lies between EL and EU, what will happen? Some electrons can travel to the upper valley. Okay, so electrons can gain energy from it and move upward to the upper valley, as I said. So as the electrons transfer to the upper valley, what happens? Since the mass is high here, so their velocity decreases and the effective mass is increased, thus decreasing the current density J, and hence we get what? Negative resistance region, okay, or negative differential resistivity. Then finally what will happen? A can be greater than this upper valley electric field. So when the applied field is higher than that of upper valley, all electrons will transfer to the upper valley, right? So once the electrons are in higher valley, they remain there as long as the field is greater than the critical value. So this is quite simple. So and then we get the actual negative resistance. So here the phenomenon was started, and here we get the actual negative resistance in this when the electric field is greater than the upper valley electric field. So this is what is the graph shown. So when this is the region above that threshold electric field, we are starting to get the negative electric field region, right? So then, as I said, the important question from exam point of view is modes of operation. So for that, you need to understand what is a domain. So now we saw that negative differential resistance occurs by applying electric field of a certain value, that is, it should be above a certain threshold, to multi-valley semiconductor compounds like N-type GAS. So what you mean by multi-valley is, we have these two valleys, right? So that's why it is called as multi-valley semiconductor device. So now it can be proved that without that derivation, which is not included in the syllabus, so I am not taking it. So it can be shown that a decrease in drift velocity by increasing the electric field leads to a formation of a high field region. So this high field region is referred to as domain. So increasing electric field leads to what? A decrease in drift velocity. Why? Because increasing electric field takes the electrons from this lower valley to upper valley. So here the mass is less, right? Therefore the electron velocity increases. So this leads to a high electric field, which is referred to as domain, and this domain leads to microwave generation and amplification, and that is what we require from the Gunn diode. So that's why this concept of domain is important. So then according to the material parameters and the operating conditions, we have Gunn diode divided into four basic modes of operation. So first is the Gunn oscillation mode. So this is so they are made so this all these modes are defined mainly as a frequency and length multiplication. So if the frequency and multiplication by length is about 10 raised to 7 centimeters per second, and the product of doping multiplied by length is greater than 10 raised to 12 centimeter per square, 10 raised to 12 centimeter square, we say that the mode of operation is Gunn oscillation mode. However, this operation is very unstable, so that's why this mode is not used. Then we go to stable amplification mode. So in this mode, again frequency length FL is about 10 raised to 7 centimeters per second. But if you see, the product of doping and length is around between 10 raised to 11 and 10 raised to 12. So if you change the doping, then we get the stable amplification mode. And then we have LSM mode, where again FLA is now about 10 raised to 7 centimeter per second, and the doping is 2 into 10 raised to 4 to 2 into 10 raised to 5. Then finally we have bias circuit oscillation mode. So this mode occurs only when there is either Gunn or LSA oscillation, and it is usually the region where the product of the frequency and time length is too small. So this FL value will be quite small here. So these are the four modes of operation of a Gunn diode. So as I said, this Gunn oscillation mode is unstable. So we usually refer the stable oscillation mode. Then on what basis we classify the modes? We can classify using this formula. So N naught L is greater than epsilon V upon E into mod of mu N. So what is mu? Is the mobility, then epsilon is semiconductor dielectric permittivity, N naught is doping concentration. What is E? It is the electron charge. Okay. So this is not that important, but I just included it for the sake of completeness. So then we have, as I said, the Gunn oscillation mode is unstable. So we mainly rely on stable amplification mode because we require stability. So in this mode, obviously FL, that is the product of frequency and length, is 10 raised to 7 centimeters per second. So what happens here is the electron drift velocity is equal to the sustaining velocity. So since this is stable amplification mode, we get sustained oscillation. So that velocity is sustaining velocity. So since they are equal, we have the T naught time, that is period of oscillation, equal to transit time. So transit time is what? The transit time of electron transit time, which we saw in transit time effect. However, the efficiency is below 10% because the current is collected only when the domain, that is the high field, arrives at the anode. So when the electron strikes the anode, that is the high field reaches the anode, then only the current is collected. So that is the reason the efficiency is low. Okay. So to increase the efficiency, what we use is the delayed domain mode. So what we do, we keep the electric field less than the threshold electric field. Because of this, what happens? The tau naught, is greater than the transit time of electron, and because of this, the efficiency increases. So what happens? This current reaches the anode earlier. So because of this, the efficiency increases because the oscillation start earlier. So this helps in increasing the efficiency of the Gunn diode. So then finally we have quench domain mode. What happens here is tau naught is less than tau t, and the field goes above ETH. So since the field goes above ETH, it is not able to reach the anode faster. So again the efficiency reduces to about 13%. But what is the advantage? That it can be tuned over the broad frequency range, means we can have a broad bandwidth. So this will be a narrow bandwidth. So we always, if we try to increase the efficiency, always the bandwidth suffers. So that is what is the trade-off which we have to have in between the modes. So these are the three modes under stable amplification mode. That is, the FL will always be 10 raised to 7 centimeters per second here. Okay. So then next we are mainly seeing impaired trapette and buried diodes. So that we'll see tomorrow. So I'm purposely going slow because we are mainly in touch with the syllabus. So that's why I'm mainly going slow.